What's up, guys? Today we're doing a video on population proportion, which we call P, sample proportion, which we call P hat, and the standard error of the proportion, or the SEP. The population proportion is a parameter that describes a percentage of a population. Parameter meaning it's not a statistic. A parameter is a fact, something that exists in a population. Sample proportion, P hat, is a statistic that describes a percentage of a sample. So instead of looking at the whole population, we're looking at a sample of a population and we're describing some percentage. Okay, and I'm going to give you an example in a minute. And that brings us to the standard error of the proportion, which we call SEP. It's the standard deviation of a sample proportion distribution. And this is going to make more sense in a minute. I'm going to do a little simulation for you. We're going to see how this works. But here's the formula, and it's on your formula sheets. Okay. The P that's inside this formula is supposed to refer to the population proportion, okay, the actual P, not P hat. However, sometimes we don't know what P is, and if you don't know P, then we can use P hat to estimate the standard error of the proportion. Hopefully all this is going to make more sense after we do a simulation here. Okay, so I brought a bag of tiles, okay? There are, believe it or not, 400 tiles inside here. It doesn't look like it, but there's 100 of each color, and there's 4 colors. Okay, and so the best way to explore this, I think, is to do a little bit of an experiment, a little bit of a trial with some of these tiles, and see how it works out. Okay, now I've already done some of it. I've written some facts down here that we need to look at. So there's 100 red, 100 green, 100 blue, and 100 yellow tiles. This means it's 400 tiles. Okay, therefore, let's take one color. Like let's say the color red. Okay, if I'm looking for the color red, the population proportion of red tiles, or P, is 100 out of 400. This is not a statistic, it's a parameter. It's a fact that there's 400 tiles in that bag and 100 of them are red. So that means P for red tiles is 0.25. In other words, 25% of the tiles are red. That's not a sample. I didn't reach in the bag and pull some out. That's actually how many are in the entire population, where the population is this bag. Everything in this bag is my population. 100 out of 400 are red. Therefore, P for red tiles is 100 out of 400, which is 0.25. Okay. Now, the SEP, I can go ahead and calculate that right now because it calls for P, not P hat, which I'm going to get to P hat in a minute. So the formula said P, 1 minus P, and this is N, where N is the sample size. Now, I haven't taken a sample yet, but what this is saying is if I were to take a sample of 40, if I were to reach into that bag and pull 40 tiles out, that means N, the sample size, would be 40. Then when I plug this formula in my calculator, I get 0.068. This number is the standard deviation of the distribution I would get if I were to do many samples, okay? And we're going to look at that here in just a second, okay? I actually did go ahead and do a sample. I reached into the bag and I pulled out 40 tiles, and I've got those tiles right here. Okay, I've got 4 stacks of 10 tiles that I reached into the bag and I pulled these out. Okay, now if we look through here, I've got 2 red in this stack. I've got 1, 2, 3, 4, 5, 6 red in that stack. So that's 8 so far. 9, 10. 11, 12. So out of this sample of 40 tiles, I pulled out 12 red tiles. So for that sample, for that one sample that I just did, P hat, remember, which is the proportion of the sample, was 12 out of 40, which is about, let's put in the calculator, 12 divided by 40 is 0.3. Okay, now P hat will change. P does not change. There are 100 red tiles out of 400 in the population. So P is 0.25. In the sample I took, P hat was 0.3. I randomly selected, to the best of my ability, 40 tiles, and out of those, 12 were red. Now, ideally, you would expect to find exactly 0.25, okay? And meaning out of 40 tiles, you would expect that 10 of them would be red. But it's not going to happen exactly that way every time. So if I do many trials of this, if I reach in there and get another 40, I'm going to have maybe 9, maybe 8, maybe 13, maybe 14. But the further away from 10 you get, the less likely it is. Maybe I do another trial and I get 10. And I do another trial and I get 13. Well, luckily for you, I went ahead and did many trials and actually did this through a simulation with random numbers. But this is a very realistic list of numbers that you could have gotten. So I reached in and got 12 the first time. Maybe the next time I got another, I put those back, got another 40 tiles, and that time I got 9. Okay, put those back. Another time I pulled out and I got 10. Okay, if I did that, this right here is, I believe, 40. This is 4 rows of 10. So I did 40 trials where each time I did a sample of 40 tiles. So this was 12 out of 40 that was red. This was 9 out of 40 that was red. 10 out of 40 were red. 8 out of 40 were red. 10 out of 40 were red. 11 out of 40 were red. Here's where the distribution comes in. The more times you take samples, the closer, if I were to take an average of all of these, what do you expect the average would be? As it turns out, the average is going to be very close to whatever P is supposed to be, which is 0.25. If I were to take an average of these, I would get a sample that's very close to 10. Okay, if the average of this would be close to 10, because 10 out of 40 would be 0.25. Okay, well, I entered some data into the calculator. Okay, so I went into my list here, and instead of typing 12, 9, 10, 8, 10, whatever, I typed that number divided by 40. So in other words, 12 out of 40 was actually 0.3. Okay, 9 out of 40 was 0.225. So instead of putting in how many red tiles I found, I put in the proportion of red tiles that I found. Okay, so I have all these entered in the calculator. These are P hat. Each one of these is P hat. P hat, remember, is the proportion in a sample that you took. Well, what would happen if I were to make a histogram or a dot plot based on this? In other words, if I were to do a distribution and see that the shape of that distribution, do you have any idea what kind of shape that might make? As it turns out, it makes what should be a very familiar shape for you. I went into my Windows settings, and since my numbers all range between 0 and 0.5, well between 0 and 0.5, these are percentages, remember, so they couldn't be above 1, I counted in 0.025 increments, because if I do 1 divided by 40, that's 0.025. So all my numbers are going to be some multiple of this. Like 2 divided by 40 would be 0.05, and 3 divided by 40. So by making 0.025 what I counted by in here, it means that any of these points divided by 40, all these things that were in my table, all of these are going to be numbers on my axis. Okay, so then when I go to graph, and I'm doing a histogram here, it's the closest I can get to a dot plot on this. Look what kind of shape that is. That's a bell curve, right? Or it's very close to one. It's close to a normal distribution. Now this is only 40 trials. I can hit the trace button and I can move across and we can look at what some of these numbers are. What do you think this one in the middle probably is? Well, as it turns out, there's 8 of them, but the data point is 0.25. That's P hat. Okay. So every trial is a data point here. If this was a dot plot, there would be 8 dots stacked up right there. It says n equals 8. So this is, I had to do a histogram, but if I were to do a dot plot, you would have 8 dots stacked up at 0.25. If I go to the right, that's 0.275. There's 6 there. Okay. So that's how this works. Go back to these vocabulary words again. 0.25 is the actual proportion of the population. 25% of the tiles are actually red in the bag. If I do a sample, I should find about 25% are red. Sometimes it'll be a little more, sometimes it'll be a little less. But if I do that trial a ton of times, like I did here, all of those trials make a normal distribution, where the mean of that distribution at the center should actually be P. Okay? This is the distribution of P hat. Every sample I do is another point on this curve. But the vast majority of them are going to be very close to the actual proportion P. Okay? Well, just like any normal distribution, this normal distribution has a standard deviation. And each of those standard deviations, I'll draw them out like the empirical rule. Each of those standard deviations, that's what this is. Okay? This SEP, the standard error of the proportion, this number is the standard deviation of that curve. Okay? And while mine doesn't look like a perfect normal distribution, you can see it actually dips down here. It's not shaped exactly right. If I were to do a lot more trials, like say instead of doing 40 trials, say I did 4,000 trials, you would find that this becomes a very smooth, very accurate normal distribution. Okay, so let's actually look up some of the things I was talking about earlier. Now, remember that in this normal distribution, or what becomes more and more a normal distribution, the more trials you do, that the mean in the center of this distribution is actually P, not P hat. This is this approximates the actual proportion of red tiles in the bag. The more trials you do, the closer it gets. And so let's look right now. Let's see how far off we are. So if I go to stat, I go to calc, and I'm going to do one variable stats. This is going to tell me the statistics for those data points that I entered. So n is 40. That's the 40 data points that I entered. And remember that each of those data points was the result of me grabbing 40 tiles and seeing how many were red. Grab another set of 40 tiles, how many are red? I did that 40 times. Okay. And then when I take those 40 proportions, those 40 P hats, okay, the mean of all of those was 0.25375, very close to 25%. And the more trials I did, again, if I did like 10,000 trials, this number would be dead on 0.25, okay? And the standard deviation, regardless which one you use, we really should be using the sample, so S, 0.0562. Now that's a little bit off from what we expected it to be, but it's not very far off. It's pretty close. We said in our formula that the actual SEP for this data set is 0.068. That's using the actual population proportion, not the P hat, but the actual 25% of the tiles are red. With a sample size of 40, we should expect that distribution of samples to have a standard deviation of 0.068. Well, this is a little bit off. It's 0.056. So it's not too far off, but it's also not too close. We would have to do a lot more trials. And the more trials we did, the closer you would see this number getting to this number. Okay, so the video is getting long. I just want to do one quick example. And that's how to find P hat and SEP. It's actually not as hard as I'm making it sound like. The actual work is easy. I just feel like it's important if you understand what these numbers mean, because we're going to be doing a lot more with them as this unit moves on. Okay, 27 out of 32 students passed a math test. Find P hat and the SEP for all students. Okay, so we're assuming that these 32 students that we looked at their scores are just 32 out of a larger, maybe it's all the students that the teacher teaches. Maybe this is just one class, okay? So 27 out of 32, that's our sample. P hat is the sample. This is a sample because the population would be all the students, okay, which we don't even know how many that is. But 27 out of 32, so our sample, P hat, our sample proportion is 27 out of 32, which is 0.84, meaning 84% passed, okay? Sometimes they may just tell you the percentage. If they tell you the percentage, that is P hat. If they express it as a ratio, you just got to divide to find out what P hat is. Now, since we don't have the actual population proportion, when we do our SEP, we have to estimate it in this case using P hat. And in our class, that's usually what's going to happen. Most of the problems, you're going to have a sample proportion, and we're going to use that with the SEP formula. Although ideally, you want to use the actual population proportion if you know it. So right here, this is P, so 0.84. This is 1 minus P, so it's 0.16. Another way of thinking about this is if 84% passed it, this is how many did not pass it, which is 16%. That's why these always have to add up to 100%. Either you did pass or you did not pass, okay? Going back to our tiles, either you had a red tile or you had something that was not a red tile. Then down here is our sample size, and since it was 32 students in our sample, then this is 32. You type all of this in the calculator, which I did here. This is how I typed it. You could use the fraction button as well, and you get 0.064, okay? Remember, the SEP is simply the standard deviation, okay? If I wanted to, I could draw out a little sketch of our normal distribution. The mean would be P hat in this case is 0.84, okay? then if I go left and right one standard deviation, that means I'm going to add 0.064 or subtract 0.064. So I can do 0.84 plus 0.064. We'll just go that far. And that's 0.904. I'm going to round it to 2 digits to make it easier. Okay, and if I went to the left, 0.84 minus 0.064, that would be about 0.77. 0.78 really. And you could go more digits if you want to. I'm trying to save room to write. But that's how this works. And you could keep going. You keep adding the SEP and subtracting the SEP in your normal distribution. Okay. And this is just like a regular normal distribution that we've been working with, where the standard deviation is actually the standard error of the proportion, because this is a distribution of samples. If I was to take a different sample of 32 students, maybe 28 would pass, or maybe 26 would pass. Okay, so maybe instead of 84% of them passing, maybe 87% or 78% or some different percentage, depending on the random sample I took. But most of them should hopefully fall around what the actual population proportion is.